A very good morning to one and all. I, Dr. G. Haripriya, HOD of Department of H&S and convener of 1 week international FDP entitled Mathematics for a Better World, welcome you all for the 6th day session. It gives me an immense pleasure to introduce our today's speaker, Dr. Maheswara Rao Valluri, who is going to address today's session on the topic Algorithmic Aspects of Public Key Cryptography. Dr. Maheswara Rao Valluri is currently an associate professor at School of Mathematical and Computing Sciences, Fiji National University, Fiji. He also obtained his PhD from Sri Krishnadevaraya University, India. Prior to this, he worked as an academician in India and Oman. He was a visiting researcher at University of Auckland. His area of interest include algorithmic number theory, computational algebraic geometry, cryptography, and quantum algorithms. He is a member of the International Association of Cryptographic Research, American Mathematical Society, and the Institute of Mathematics and its applications. He served as head of school mathematical and computing sciences and associate dean at College of Engineering and Science and Technology, and also elected representative of the University Executive Council. He also served several times as chairman of academic and examination boards. He also served as Senate member of the university. He has served as technical committee member of several international conferences and also reviewer of international journals. He is currently editor of Mathematica Sciences Today magazine of Andhra Pradesh and Telangana Society for Mathematical Sciences. He also jointly received Best Paper Award in 2016 for his Quadratic encryption work from World Congress on Industrial Congress System Security 2016, London, UK. He has total of 23 publications. We are very fortunate to have you, sir, for this session and welcome you once again. I request you to take over the session, sir. Thank you, sir.
Thank you, Dr. Haripriya. Can you see the screen now?
Yes, sir. It is visible, sir.
Okay. Good morning to all. I would like to give today my talk on algorithmic aspects of public key cryptography. So I would like to thank these people who contributed to this area. In my view, the basic requirements in human life are privacy, security, and trust. In this talk, we focus more on security aspects. What is cryptography? Cryptography is the science of secret writing by dictionary definition. We can also say that is the study of principles and techniques for secure communication in the presence of third parties called adversary. There are a lot of popular cryptographic algorithms, mostly used to protect emails, credit card information, iCloud data, corporate data, as well as to build security layers, etc. The design of public key cryptographic protocols heavily relies on computational hard problems, means that computationally has to be essentially impossible on a classical digital computer. So what are the key features and purpose of cryptography? Cryptography provides security features such as confidentiality, integrity, authentication, and non-repudiation. I think I don't require to elaborate on these terminologies. Everyone is familiar. So let me give about cryptographic primitives. There are mainly three categories of cryptographic primitives. Symmetric key primitives, in which mainly we have two private key ciphers, message authentication codes. And second important one is hash functions. Third one is public key primitives. In public key primitives, we have three main: key exchange protocols, public key ciphers, and digital signatures.
Excuse me, sir.
Yeah.
Sir, will you share the PPT, sir? They are not visible, sir.
So that's what I asked you.
Yes.
Can't see those. Yeah.
Now it's okay,
Can
sir.
you?
Yes, sir.
All right. Thank you. So I'm giving only few important cryptographic primitives. There are many variants. Let me give framework for private key encryption. In a private key encryption, there are two players, say for instance, a sender and receiver. So in order to send via public network or message or a data or information, anything, if you send directly through public network, anybody can read. So you want to maintain confidentiality for the data. What you need to do? You need to encrypt the data. To encrypt the data, we need to use one secret key. That's called secret key. Then using a key, we can encrypt like you have a box. You can put it in a box, something, then you can lock it using a key. Then you can send the box to sender. In order to open the box, what he needs a receiver, he needs to have same key. If he has a key, then he can open and he can read it, whatever inside the box. Same approach we can use in the private key encryption. So in the private key crypto system, we use a single key in which both the sender and receiver have. What is the advantage using private key crypto system, which can provide confidentiality to the data or information? There are many private key algorithms which started. We can recall Enigma, one Germany used during World War II, AES, Advanced Encryption Standard Algorithm, DES, Data Encryption Standard Algorithm, Triple DES, Blowfish, Twofish, Salsa, MAC. These are all categories of private key cryptographic algorithms. So we are not going to focus on this area today. Another important one is hash function. Hash function works like this. You can take a bunch of data which is unknown size, maybe a textbook, anything, arbitrary size of the data, which takes as an input and provides output of certain length. So that's the property of hash function. You can look at this picture. You can say this message using hash function, it can output certain size of data, so certain length data. So mathematically, how we can define the hash function? Hash function that maps data of arbitrary size to a bit of fixed data. Precisely, this is a function which takes the binary data of unknown size and it generates output in terms of bits of a particular length. There are significant hash algorithms, say MD5, message digest 5, SHA1, SHA3, etc. But I recommend to use SHA3, which is a collision-free hash algorithm. But what is the use of hash function? Hash function can provide security feature of integrity for the data. So that is the advantage. Anything that you want to provide integrity to data, you need to use the hash algorithms. So I'm also not going to focus on hash functions. Third one is public key crypto system. As I mentioned, in public key crypto system, I focus mostly on three cryptographic primitives. One is a key exchange protocol, another one is encryption or cipher, third one is digital signature. How key exchange protocol works? There are two participants in the protocol. One is sender, another one is receiver. The sender has two keys. One is private key, and you can compute a public key using a mathematical function. Then, so for each private key, there is a corresponding public key. So similarly, the receiver or second party also can have a private key and corresponding public key, which is generated using a mathematical problem. Then, so they can start the protocol like this. The A can have a secret and B can have a secret. Then they can generate public key. So this is the public key. So E also can generate public key. They exchange public keys. Then they can use their corresponding secret keys to compute the common secret shared key. So you can use A can use his secret using the B's public key. Similarly, B can use his secret key using A's public key, and they can have common shared secret key without sharing their private keys. So this is very important protocol. Another one, encryption. We have two participants here. One is sender, another one is receiver. So in order to send a message in the form of encryption over a public network, so the sender should have receiver's public key. Receiver should have has two keys in a public key crypto system. One is a private key and corresponding public key. Private key and corresponding public key. So public key is a key which can be shared to anybody, but private key he keeps himself. So look at this framework. To send a message in the encryption form, the sender first collects the public key of the receiver. For instance, in another words I can give, in order to send a message or in order to send an email, what you need to do, you need to have email ID of the receiver. So email ID is a public. If you know the email ID, can you be able to find it corresponding password for the associated password to the email? You can't, right? So the password is more like private key. So you can encrypt the message using receiver's public key and send the ciphertext over a public network, so that nobody can read what is the content of the message. Then after receiving, the receiver can use his private key to decrypt the message to obtain the original message of the sender. So this is another framework which is called public key encryption or public key cipher. Next one is a digital signature. Digital signature can provide security features of, one is confidentiality, integrity, authenticity, and non-repudiation. In a classical days, we have a signature system, a paper pen based signature system. So it is just an analogy. We make it a digital system for the same concept. So in the digital signature system scheme, again, we have two participants. One is sender, another one is receiver. So sender, this is the public key digital signature. Sender can have two keys. One is private key and corresponding public key generated using a mathematical function, right? Then in order to sign a document, the sender uses his private key to sign the document. Then after signing the document, he will send to the verifier the documents, signed documents. In order to verify the documents, the verifier uses sender's public key. So then if verification works, he accepts, otherwise he rejects. That's how it works, the digital signature. So these three are the main frameworks for public key primitives. Now, let me go a bit in depth. Public key crypto system uses two keys we know. One is a public key, another one is a private key or secret key. The idea proposed by Merkle, Diffie, and Hellman, who received Alan Turing Award winner Alan Turing Award in 2015 in 1976. This idea was also proposed by James Henry Hillis at the Government Communication Headquarters, UK in 1970 under the name of non-secret encryption. So the same idea was discovered before, but it was not published. And Diffie-Hellman first proposed in 1976. Then, so any public key crypto system works based on the computational odd assumptions. There are two types of problems. If you are familiar with the computational complexity theory, one is p-type problem, polynomial type problem. Another one is np-type problem, non-polynomial type problem. Polynomial type problem, a problem which has a solution and easy to find the solution. Non-polynomial type problem, a problem which has solution but difficult to find the solution. So one of such computational odd assumption, odd problem is discrete logarithmic problem. What is discrete logarithmic problem? I hope you are familiar with a bit number theory and algebra. Let G be a subgroup of a finite field of order P, Galois field. We take P size 1024 bits length. Given a primitive root G, which is a member of a subgroup, and Y is a member of a subgroup, such that Y equals to G power X mod P. It is hard to compute X. For instance, let us take a finite field of prime order 40961. Take a primitive root G, which equals to 367. Now, I give the Y value 22,471 and a primitive value, which is 367. I ask you to find XA value. Can you find? It is hard to find. But manually we can try by brute force search. So in this case, the answer is X value is 2354. I could find by brute force search. But to tighten the security system, we use a large prime. What is the size of this prime? The prime is just here 5 digits. In practice or in real-time applications, we use around 200 to 300 digits length prime number. So that can provide. For the case of 1024 bits, it would be, I think, roughly 300 digits, more than 300 digits length, which is equivalent to RSA 1024 bits. Right. Let me give how Diffie-Hellman key exchange protocol works. FE, a finite field of prime order 40961. I have taken small numbers to ensure that you understand how system works. Take a primitive root G 367. Then it is a simple arithmetic, you know that. Take a secret XA equals to 2354 and compute this simple modular arithmetic G power XA. You know X value. You know XA value 2354. You can, you know, G value 367. You can multiply G 367 2354 times. Then apply the modular 40961. Whatever the remainder you get, that is the Y value. So here, if you know the X value, you can easily compute the Y value. But if you know the Y value and G value, hard to compute X value. This is called discrete logarithmic problem, because you can apply both the sides logarithm. You can, and you apply logarithm, log Y base G equals to X. So that's why we call. And also we are using discrete values. We call it discrete logarithmic problem. Similarly, Bob chooses a random secret XB, which is a 435 from the same finite field, and computes. He knows what is XB value. He knows how to compute YB value. We can do that. This is a very simple arithmetic. Anybody can do that. So after that, what they do, they both exchange public keys. Here, you can look at that. XA is the secret key of Alice. XB is the secret key of the Bob. And then using secret keys, they could compute the corresponding public keys YA, YB. So YA, YB public. So we can use public network to exchange. No, not a problem. But there is a middleman attack in this process. But we need to ensure we share authentically the public keys as well in practice, right? I am not going to talk that part now. Then, so you can send YA, YB, YA to Bob, YB to Alice. So once Alice receives the public key of the Bob, YB, then using her secret key, she can compute again YB power x power a mod P. So then she can obtain. Similarly, Bob can do. Bob obtain public key of the Alice, YA, and he can use his secret key XP, then can compute. This is the commonly said secret key. In this protocol, you can notice they haven't accessed anymore their secret keys. However, they could compute the common said secret key. This is the protocol mostly we use in even SSL certificate, web browsers, all these things, handshake protocol, right? So this is the first idea. It's a groundbreaking idea in cryptography in 1976. Next one, later in 1985, Algomal proposed using a discrete logarithmic problem, an encryption system. Let me go. In encryption system, we have three algorithms. One is a key generation algorithm, another one is encryption algorithm, another one is decryption algorithm. In a key generation algorithm, Alice and Bob agree to use a finite field. I used frequently the same field, finite field, and a primitive G. Then Alice chooses a secret XA and computes the corresponding public key YA. So same as the Diffie-Hellman key exchange protocol approach. For instance, I have taken the same field and same primitive and same secret. Then we know how to compute a public key of Alice. So you could compute this. Then XA is the secret key and public key is YA. Now, next step, Alice knows secret key and corresponding public. You can see that here we used computational hard problem. Once you could break the computational hard problem, means given public key YA and primitive and other set of parameters, if you are able to find a secret key, you can totally break the security system of discrete logarithmic based problems. Discrete logarithmic based cryptographic protocols. Now, encryption. To send a message in an encryption form to Alice, the sender is Bob. You will use an ephemeral key R, which is also from the same finite set, and computes cipher C1 equals to G power R, and G2 equals to M times YA. YA is a public key of the Alice power R. Then can compute C1, C2 as ciphers, ciphertext C1, C2. Then Bob can send to Alice. So this how this process happens here. So same finite field, and primitive G value. Then he has taken R 435, a message 4569, which is also from same finite field. So the encryption process by Bob C1, he takes R, an ephemeral key randomly, then he can compute and the C1 value. This is C1 value 869. C2 value using the public key of the Alice. Public key of the Alice, we know. This is the public key of the Alice, YA. So public key, then message 4569 times 22,471 power 435. Then you do this modular function, then you can obtain C2 value. Now we are hiding the message here. We already encrypted the message. We have ciphertext C1 and C2. And we send these C1 and C2 via public network to the receiver. Who is the receiver here? Alice is the receiver. After receiving ciphertext C1, C2, Alice can use her private key to decrypt the message. So this is the computational M equals to C2 times C1 power x minus a mod p using our secret key xa. So in this process, you can do simple this computation and obtain the original message. Very simple. So mostly this the basic level of arithmetic. Next one is digital signature. These are the algorithms we use in practice even now. Okay, in digital signature algorithm, which is a standardized algorithm by NIST. In this, we have three algorithms again. One is key generation algorithm, another one is signing process, then verification process. In digital signature algorithm, in any of these algorithms, choosing recommended parameters, very much important, because if we don't choose properly the parameters, security will be compromised. The attacker has scope to attack the system. A signer chooses two primes, P and Q, such that P is congruent to 1 mod Q. In practice, we choose P in the size 2 power 1000, between 2000, 1000 to 2000, 2 power 2000, and the Q value 2 power 160, 2 power 320. Then the signer chooses a primitive G for selecting for certain reasons, computational reasons, and also not to provide any scope to security compromisation. So recommended approach for computation G equals to G1 power P minus 1 by Q for a primitive root G1 in GP. The signer chooses signing key, private key, and computes a verification key, or public key, such that y equals to G power x mod p. This is as simple as, discrete logarithmic problem. Then the signer publishes verification key, which is open to anybody who can verify, that is a public key, and keeps secret signing key x. So as simple as this is discrete logarithmic problem in the key generation process. In order to sign a document or a message, the signer follows the following steps. 1, chooses a message in this range, then choose a random integer from this Gallus field, and computes G congruent to G power or mod P mod Q. Then computes sigma equals to M plus X times Z. What is X here? sorry, something missing here. This is M is a message, G we obtained from here. There is a step missing, the hashing part of the message, times R inverse mod Q. Then the signer sends signature pair G and sigma to our verifier. Upon receiving the signature pair sigma, G and sigma, verifier does the following steps. He computes first V1, M times sigma inverse mod Q, V2 equals to Z times sigma by G, Z by sigma mod Q, and accepts G power V1 times Y power V2 mod P mod Q equals to sigma. Otherwise, he rejects. So these are all simple arithmetic as well. I haven't provided any example here. This is the whatever we have discussed so far based on the discrete logarithmic problem. If you have any questions, you can raise now. Next, I can move to integer factorization based problems. Integer factorization problem based cryptography. If you have any questions, you can raise now. If no questions, I can proceed. No? Okay. Next, RSA public key crypto system. Ron Rivest, Edi Samir, and Leonard Edelman is the most famous public key. RSS is the most famous public key crypto system announced at MIT in 1977 after Diffie-Hellman proposed key exchange protocol. The same scheme was also invented by Christopher Cox at the GCHQ UK in 1973. This RSA system relies on integer factorization problem. What is the integer factorization problem? Given two prime numbers P and Q, then we can easily compose. For instance, I have taken here RSA 1024 bits. P is a prime, this is the prime, and Q is another prime. Then if you know two prime numbers, we can easily compose them, that is n. But given the composite number n equals to pq, if one asks to find p and q, computationally hard for large numbers, even for computer. Even it takes millions of years to compute a digital computer. Okay, so this problem is called integer factorization problem. How we can use integer factorization problem in a cryptography? So RSA already constructed a encryption and a digital signature based on integer factorization problem. I first give encryption system. Again, in any encryption system has three algorithms. One is a key generation algorithm, another one is encryption, another one is decryption. So in the key generation process, we take two prime numbers. I have taken small numbers, p equals to 11, q equals to 13. Then we can easily compose n equals to pq, which equals to 143. If I give 143 a composite number, if I ask you to find p value and q value, it is hard for you, right? So it is easy, but since these are small numbers, for large numbers it is hard even for computer. Then we compute Euler-Tocian function pi of n, which equals to, since n is a composition of two primes, p minus 1 times q minus 1 is a Euler-Tolchian function, which is in this case 120. Then we choose randomly a number e from within the range of Euler-Tolchian function such that GCD of or the chosen number e and Euler-Tolchian function must be co-prime. Then compute d value such that d is equivalent to 1 by e mod of Euler-Tolchian function. So yeah, e is a public key and d is a private key. If I give even d value, sorry, if I give e value, if I ask you to find corresponding public key without knowing either Euler-Tolchian function or factorizing the composite, very difficult. So the security relies on either finding the Euler-Tolchian function. You will again finding the Euler-Tolchian function relies on the integer factorization problem. So even for computer, it's not possible. There are certain techniques to find some level of sizes of composite numbers. I think so far attempted 700 something bit size composite number, which is there in the, you can look at Wikipedia. But even though it takes maybe more than 2 days, 3 days. Then RSA algorithm, encryption algorithm, the public key we know, NE, E value 7, it is a public key. To encrypt what we need, to encrypt a message, we need receiver's public key. We know receiver's public key is 7. We know message m equals to 29, which is a co-prime 2n. Then you can compute a ciphertext c equals to m power e mod n. Mod n is open, n is open, right? Composite number. M is a message, m power e. Then you can obtain a ciphertext 94. The original message is 29. We encrypted into 94. Then we are sending through public network. In the decryption process, the receiver uses its private key. What is his private key? That is D 103. So same process as a encryption process. Simple. M equals to C power D mod n. C we know ciphertext, which equals to 94, power D value 1 power 3 mod 143, which can generate the message. So these are all very, very simple, but very much useful for the security purpose. Basic number theory. Next, let me give RSA digital signature. In RSA digital signature, particularly in key generation algorithm, a signer chooses two large primes P and Q and computes their product n equals to PQ. Yeah. Simple as before. And also you can compute verification key or public key E, and you can choose verification key and computes the signing key or private key. And here Euler-Tolchian function same as above, pi n. Then in order to sign a document D, first you will use a hash function. Why do you want to use hash function here? Why can't you straight away sign the document? So to provide integrity to the data means anyone altered the information or not, to check it, this hash function can do this process. So we use always in digital signature signing process, we use a hashing algorithm to provide integrity to the data. So H equals to H of D. Then we sign using the private key to obtain the signature sigma. Sigma equals to H of D. h of d power d, this d is a private key model. Then the signer sends a pair of documents as well as signature d and sigma to the verifier. Verification process is also very simple. A verifier verifies the validity of the signature using the verification key of the signer by computing. First you will do the hashing process, then you can compute using the verification key. If this relation works, then he accepts the signature, otherwise he rejects. So the arithmetic process works like this. D E equals to 1. It works like this. Now, any question? We have completed digital signature, discrete logarithmic based cryptographic protocols, as well as integer factorization based cryptographic protocols. Next one is quadratic residues and quadratic reciprocity. I focus only of quadratic residues. How can you tell whether a given number A is equals to a square mod P? Suppose this, if I ask you whether 1217 is a square mod 40961. One way for find you to answer my question is by checking each square mod 40961. Let us see. We can see 1 square 1, 2 square 4, then keep going. So if you are taking the value 9647 square congruent to 1217 mod 40961, that's the place where you can trace it. What if it does not exist? That's a quadratic non-residue, right? So this is also a tricky problem, computational odd problem. You can only find this value by using brute force technique here, right? So let me give quadratic residues and non-residues. Let P be an odd prime number. Let A be a number with P doesn't divide A. Then we say A is a quadratic residue mod P if A is a square mod P. That is, if there is a number C such that C square congruent to A mod P. If A is not a square mod P, then that is, if there exists no such C, then A is called quadratic non-residue mod P. I give these two situations. The number 968 is a quadratic residue mod 1223. You can see that since 453 square congruent to 968 mod 1223. Another situation, the number 209 is a quadratic non-residue mod 1223 since there is no such C exists. So there is no C value. This is quadratic non-residue case. So it's a clear what is quadratic residue, quadratic non-residue. Now using this idea, Safi Goldwasser, Macaulay proposed an encryption system I can discuss later. Then let us discuss legendary symbols for quadratic residues and non-residues. There are three expressions here, a straightforward definition. Let P be an odd prime, then legendary symbols of A is a quantity. A divides P defined by the rule A divides P equals to 1 if A is a quadratic residue mod P, 0 if P divides A, minus 1 if A is quadratic non-residue mod P. This notion is very much important. Then how can you find? We can use Euler's criteria. The integer A and A and P, the integer A, GC A and P must be co-prime, missing that, is a quadratic residue mod P for an odd prime P if and only if A divides P, or which equals to A power P minus 1 by 2 congruent to 1 mod P. If it is quadratic residue. If it is not non-residue, then it is minus 1 mod P. So you can use this technique, Euler's criteria. Then for quadratic residue and non-residue computational odd problem, Goldwasser Macaulay designed or constructed an encryption scheme. In 1982, Sophie Goldwasser Macaulay, who were honored by Alan Turing Award in 2012, developed an encryption scheme which we call Goldwasser-Macaulay public key encryption scheme. This scheme works based on the quadratic residue problem. How can we define the computational odd problem, the quadratic residuicity problem? Let P and Q be two prime numbers. We keep both secret, and we can compute RSA composition n equals to PQ. For a given an integer, determine whether A is a square mod n, that is, determine whether there exists an integer U satisfying U square congruent to A mod n or not. So this is called quadratic residuicity problem. Now, let me give the Macaulay's encryption. The key generation process, like same as RSA, choose two primes P and Q. We have taken here, for instance, P equals to 2309 and Q equals to 5651, such that meeting the Euler's criteria, where A value equals to this large number. And compute the n value, we can do that. Then the public key is n and private key is a pair of P and Q. To encrypt a message, which is from the set of bits, zeros and ones only, not from integer set, choose a random R1 for m equals to 0 and R2 for m equals to 1. Right? So the R value must be in the range of n. Then we compute a ciphertext C equals to R1 square mod n, which gives this value if m equals to 0. If m equals to 1, the message in terms of bits, zeros and ones. If it is m equals to 0, then we use this relation. If m equals to 1, we use this situation. Then we can obtain ciphertext C's. Once we send ciphertext, in order to decrypt the ciphertext, we use this technique, Euler's criteria, to recover the original message. Any questions here? This is Goldwasser's and Macaulay's encryption scheme. Any questions so far?
No, sir.
Okay, thank you. Next level. Furthermore, I use elliptic curves. Elliptic curves are a class of Diophantine equations. When we talk elliptic curves, I always quote Serge Langs, who said, "It is possible to write endlessly on elliptic curves. This is not a treat." What is elliptic curve? What is the expression for elliptic curve? Let me give the long V-Strauss form of an elliptic curve. The long V-Strauss form of an elliptic curve E over a field K is the set of points in a projective V square algebraic closure K bar satisfying a homomorphic equation of the form this expression, this equation, lengthy, where we have total 5 constants which are from algebraic closure K bar. The point O, which is called point of infinity 0, 1, 0, which is I have to draw the picture for this. Then the discriminant delta, this you need to compute this. and we also have J invariant. So from long form to short form, we can map it. An affine form, short form of elliptic curve E over a finite field FQ, where Q is a prime, is defined as follows. So elliptic curve is a set of points, pair of points, coordinate points from field which satisfies the relation y square equals to x power 3 plus ax plus b, and also the point of infinity O. So this is the elliptic curve. When we draw elliptic curve for this short form, it appears like this. So like for any quadratic equation, we can also find discriminant for, this is a more like cubic equation, we can find discriminant, and also we can find J invariant. These are the new terminals, perhaps if you are new. Then how we can use this elliptic curve in crypto? The beautiful property here, when you add 2 points P and Q, these two are the rational points on elliptic curve. When you add these 2 points, not equals to this R value. It's a R value reflection of minus R. So how do you compute this? Using slope and tangent approach. We have 2 coordinates, point P and Q. Then one can compute the third point on the elliptic curve using slope and tangent approach. And also we can compute doubling point. So means when you add P, again P times, again add P, n times you can add it. So we are choosing only doubling point. If you have a rational point P, then you can add another time P. Using again slope and tangent approach, you can compute these values, these coordinates x2p, y2p. This is more into, I can say that, yeah, primary level maths, not primary, secondary school level maths, or intermediate level maths. Right. Elliptic curves have rational points. Those rational points satisfies the group structure. Let elliptic curve, let EFQ be an elliptic curve over a finite field, then the following properties hold. One is, if you choose any rational point on elliptic curve and a point of infinity, then you add those P plus O equals to P or O plus P, which is called identity property. Similarly, when you add P, when you take any rational point on elliptic curve, then inverse negative P. Here, the group operation is addition, not multiplication. It is an additive group. P plus minus P equals to O equals to minus P plus P, which is inverse property, and also it satisfies associativity and commutativity. So basically, elliptic curve over a finite field is a group with respect to addition, is a commutative group with respect to addition. Right. The important thing is, when we take this elliptic curve, if you don't take a finite field, then this curve you can draw, it will approach to infinity, the point of infinity. In a cryptography, we need finiteness. We can't work on infinite set or infinite group. We always work infinite group or infinite field. We always work on finite field or finite ring or finite group. We don't work on infinite set anymore for cryptography. So if we set a bound for this elliptic curve using Galois field, then how do you find the number of rational points on this elliptic curve? So it is a challenging problem. The Assays Theorem says that for an elliptic curve E defined over a finite field Fq, so the cardinal T represents the number of rational points on the elliptic curve, which is in this bound q plus 1 minus 2 square root q less than or equals to the cardinality less than or equals to q plus 1 plus 2 square root q. Then, do you have any algorithms? Do you have any polynomial time algorithms to compute the number of rational points over a finite field? We do have this algorithm, which takes order log q power 4 operations to compute. For instance, if we take an elliptic curve, y square equals to x power 3 plus 3x plus 5 over a Galois field 17, then usually if we take multiplicative group, if we take 17 as a prime Galois field, we will have p minus 1, means 16. But in this case, 23 rational points. So by Assays Theorem, it is within this bound. What are those 23 rational points? You can see, you can substitute any of these x coordinate and y coordinate. This relation satisfies over Galois field 17. Right? Now, this is whatever we have discussed so far. It is about elliptic curves. Let me give elliptic curve cryptography. Elliptic curve cryptography was proposed by Victor Miller and Neil Cobridge in the same year, independently, 1980s. Elliptic curves are very powerful cryptographic tools for providing security, which are widely used even today in Bitcoin, citizen cards, and SSL certificate, TLS, so forth, including WhatsApp and Signal apps. How do you define elliptic curve was not discrete logarithmic problem? We take elliptic curve over a finite field. We also set up parameter prime p q we have taken here 102 for bits. Then we take we know a rational point p. We can add a rational point n times, and we apply mod q to obtain another rational point q. The trick is, which we can write q equals to n times p. Means p has been added n times. Then it is hard to compute the n value. How many times the p has been added, which is a computational hard problem. So how do you compute elliptic curve discrete logarithmic problem? We can compute the polynomial times, means order 2 times log 2 base n, or not necessary to use this 2, log 2 base n point operations. So we can use this algorithm, set q equals to p and r equals to point of infinity, use while loop, then you can run this while loop to obtain np value. So it is a polynomial time algorithm. Then, are there any algorithms that can crack? Many of researchers attempted to crack this problem. There are 3 methods that I would like to explore now. One is a brute force. Using brute force means searching for all possibilities, in which if you put the security parameters of q, now Galois field size, so which takes order q operations. If you use the polar draw method, which takes a quadratic which takes a order square root q operations on a classical computer. In another method, baby step gain method, in which one needs order q power 1/4 steps. So none of these polynomial time algorithms, so it is hard to break elliptic curve discrete logarithmic problem over using classical computing. Now, elliptical version of Diffie-Hellman key exchange scheme, which was proposed by Victor Miller and Neil Kubic. Just an analogy to, since elliptical is an additive group, they replaced multiplicative group by elliptic group. Multiplicative group by additive group. So we choose an elliptic curve, y square equals x power 3 plus 7x plus 29, and over a field, used frequently the same field, and we take a rational point on the elliptic curve. No, sorry, this should be E. It's not on a field. It should be on elliptic curve, since it is a rational point. Then choose a secret NA. That's fine. Then compute P, add P, the rational point P, on the elliptic curve NA times to obtain QA, which is also a rational point on the same elliptic curve. This QA is a public key of Alice, and NA is secret key of Alice. Similarly, Bob can do the same computational process to obtain his public key QB and keeps his secret NB. Then, same as Diffie-Hellman key exchange protocol, here also they exchange public keys by a public network. What are the public keys? This coordinate QA and QB. Once they're exchanged, then Alice can use her secret key NA to add QB NA times to get common shared secret key. Same way Bob can do. So this is the commonly shared secret key. So this is a elliptic curve version of Diffie-Hellman key exchange protocol. Next one is same as multiplicative group. We can also construct elliptic version of Algomal encryption scheme. Nothing new, just a replacement of the group structure. Alice and Bob agreed to use elliptic curves, same as this, and they can generate public keys and private key. I have taken example. Here n equals to 24, key public key is coordinate. You can compute. P is added 24 times to obtain this key value. If we give Q value, if we give the Q value, it is hard to find NA value for anybody. Hello.
Airtel
Sir, excuse me, sir.
Yes. Can
Sorry
you
for
hear
the
me?
disturbance, sir.
Shall I
So
continue?
due to some network issues,
Okay,
so you
shall I continue?
continue this program, sir.
Okay. So encryption, in order to encrypt a message M, which is a rational point on the elliptical, Alice chooses an ephemeral key R and computes cipher C1 and C2, same as Algomal in the case of multiplicative group. So this is the example. You can look at this example. We have elliptical coordinate rational point. Then we have R value, message M. Then C1 can be computed and C2 can be computed. Then the decryption process, upon receiving C1, C2, Alice computes C2 minus N times C1, which equals to M, using our secret key N. So the process, we know C2 equals to this coordinate point, C1 equals to this. So we know secret key N equals to 24. Using 24, can record the original message. So another important one is digital signature, AD25519. Means we take a particular prime number, 2 power 255 minus 19. This one is the robust version of elliptical discrete logarithmic problem, ECDSC, also known as AD25519, Edward curve, which was proposed by Daniel et al. In 2005. In this, we use a twisted Edward elliptical over a finite field, which is defined as minus x square plus y square equals to 1 plus d times x square times y square, and the point of infinity with the d not belongs to 0, 1. Then we find point addition. If we have two coordinates xp, yp, and another coordinate point, coordinate q, then we can compute point addition using this relation. So there is a technique again to find it, and a doubling point using this. So the recommended parameter in this case for q equals to 2 power 255 minus 19, and the d value is a particular size, particular value. Then in this, so we use a bit key for security reasons. We take a secret key is a b-bit string s, then hash it, then whatever the obtained hash value you can use for computing the q, that is using the elliptical discrete logarithmic problem. Then in signing process also, a lot of technical involvement there. To sign a message and determine again, hash it, the message and also the key that you have chosen here, and to obtain R. Then you can compute using this elliptical discrete logarithmic problem, this R value. Then you can compute this. We also use hash function, which takes arbitrary size to a particular length. Then you can obtain the string RS as a signature. In the verification process, more or less, we do this computation again, same as certain computation, same as signing process. Then we verify this relation. Right. So these are the number theoretic based classical public key cryptographic algorithms. Most of these, once a quantum computer is available, which are not secure, because Peterson proposed a polynomial time quantum algorithm for integer factorization problem as well as for discrete logarithmic problem. If a quantum is available and if you are able to implement these Peter's algorithms on quantum, we can break the integer factorization problem as well as discrete logarithmic problem. And also variant of Peter's algorithms even for elliptical discrete logarithmic problem. So Peter's algorithm and its variants are big threat to number theoretic classical public key cryptographic protocols or schemes. Another significant algorithm is a Love-Grover's algorithm. He proposed a polynomial time quantum algorithm for a quadratic speedup search technique, which can be used in many of cryptographic algorithms, particularly for even in hash functions and also symmetric key encryption algorithms. So these are the significant quantum algorithms to affect cryptography. What if quantum computer is available and also can implement these Grover's algorithm as well as Peterson's algorithms and variants, then we can crack mostly used cryptographic algorithms. Then now recent trend, I am not going to further to discuss this. Post-quantum crypto. Post-quantum crypto is a crypto system that can work on a classical computer and can be resistant to quantum attacks. So there are many mathematical platforms. One is lattice-based crypto, multivariate crypto, hash-based crypto, code-based crypto, super singular elliptical, isogeny-based crypto, non-commutative based crypto. So these are the areas, hot topics for research as well, right? So any attention, any questions, you can ask me now. Hello. If there are any questions.
One participant asking one question, sir.
Yeah. Shall I close this or do you want?
Sir, okay. One participant asking question, sir.
Yeah.
What is the latest key exchange protocol that is in practice? Shall I once again repeat, sir? What is the latest key exchange protocol that is in practice?
What do you mean? But mostly we use elliptic version of Diffie-Hellman key exchange protocol because it provides a better key size compared to Diffie-Hellman classical key exchange protocol. However, the modern we do have even lattice based. The problem with this, we have to use heavy key sizes and performance issues. We are not sure whether industry using all this, but there are certain proposals, some proposals for post-quantum based, as I mentioned that for key exchange protocol or key encapsulation mechanism, many recommended to use lattice-based systems, particularly for encryption, NTRE encryption, which is a much more secure and better system. But it depends on the industry. Hello?
Okay, sir.
Even if someone is interested, they can use a super singular elliptical based key exchange protocol, but they are not well analyzed in terms of security and other computational aspects, still under review process for standardization by NIST. Yes, please ask second question. Hello? Hello? Hello?
Sir, thanks for explaining about hash functions, a public key cryptography system, digital signature, sir. You have explained very well, sir. Thank you so much, sir. And it's time for out of time, sir. On behalf of Day-6 Institute of Technology and Department of Engineers, I extend a heartfelt thanks to Professor Dr.Maheswara Rao sir for the amazing session and sharing a vast knowledge on algorithm aspects of public key cryptography. It's an honor to offer vote of thanks on the last day of FDP on behalf of Legendry department. I extend my hearty gratitude to all the speakers for sharing their valuable resources with us on this 6 days FDP in mathematics. We have been fortunate to have renowned persons from all areas of academics. I extend my generous thanks to management for their instant support and guidance in organizing the FDP. I also thank our principal for leading supervision at every point of time. My grateful thanks to co-conveners, coordinators, and technical support system admin members for provision of smoothing functioning of the sessions on all the 6 days. A special thanks to Mr. Sivaya, co-convener of this 1 week FDP, for his continuous involvement from day one. Further, a big thanks to all the participants, faculty of various colleges for their active participation in making the FDP a success. Thank you one and all. Thank you.
Thank you, sir.